Okay, these, I'm going to work maybe 3 buffer problems that are, I would say, somewhat challenging, not as straightforward as the others that I worked. And this would be the first one of that type. So this problem, I guess, gives you a heads up. It tells you a buffer. And again, anytime there's a problem where you either read the word buffer or you can tell by reading what's in it that it's a buffer, you want to go ahead and write the Henderson-Hasselbalch equation to show that you understand what type of equation you're supposed to use to calculate buffer problems. Probably the most important thing to remember about Henderson-Hasselbalch is that the concentration of the conjugate base goes in the numerator and concentration of the original acid in the denominator. Make sure you don't mess those up. It's very easy to do in some cases. Some problems will even trick you by giving you this ratio in an upside down form, so just be on the lookout. All right, so what do we know so far? We know that the pH that we want is 5, so I can plug that in for pH. Okay. We can calculate pKa because we have the Ka value. So let me go ahead and take the minus log of the Ka so that we can calculate what the pKa is. And that is 4.74 is the pKa. And so we can go ahead and plug that in. And what information do we have about either the conjugate base or the original weak acid? We know that the conjugate base is going to be sodium acetate. That'll be our conjugate base. And acetic acid. So here's our acetic acid. You hopefully will remember from the Henderson-Hasselbalch equation that even though it says concentrations, that you can either put concentration or you could have moles of each because the units are going to cancel anyway. So either moles or molarity. So moles is usually easier to work with. And so what is, I'll work this out down here, 0.5 liters times 0.2 molarity, or moles per liter. And so that means that I have 0.100 moles of acetic acid, which happens to have a formula of I guess it's usually, we usually put the H in the front, so so I don't confuse people. There. All right, so we have 0.100 moles goes in the denominator, and we are trying to solve for the amount of conjugate acid or conjugate base to add. So let me get a fresh page and move on to that. All right, so this is what we have so far, and we are trying to solve for the moles or concentration of the acetate ion, which is the conjugate base. So what are we going to do first? Just math at this point. Subtract 4.74 from both sides. Now we've got to get rid of log. It's log base 10, so we raise both sides as an exponent base 10. So 10 raised to the 0.26 power, and the 10 over here is going to obliterate the log. So 10 raised to the 0.26 is concentration of, actually it's not going to be concentration, it's going to be moles, but divided by 0.100. So let me go ahead and see what 10 raised to the 0.26 is. No, that's not right. And that is 1.82. And the last thing we're going to need to do is multiply both sides by 0.1. Okay. And so we have that X, or the amount of conjugate base that we need, is 0.18 moles. Okay? And that is the answer to that one, using Henderson-Hasselbalch. And I just remembered that the problem asked for grams instead of moles, so obviously the next step would be to multiply 0.18 moles by the molar mass of the acetate. So I'm not going to do that here, though. All right, here's another real common type of somewhat challenging buffer problem. Now, when you read this, you may not realize that it is a buffer problem, and that's probably the biggest catch in this one. So what do we have? We have a weak acid. It's acetic acid. We know it's a weak acid because it's not one of the 6 strong ones that you are memorizing, hopefully. And instead of combining that with its conjugate base, which would be the acetate anion, okay, they throw in sodium hydroxide. So it may not be immediately obvious to you that it's a buffer. It turns out that this is a relatively common way to make a buffer. You add a weak acid and then you add partial amounts of a strong base so that some of the weak acid is converted to its conjugate base. Let me show you what I mean. If we put acetic acid in the presence of sodium hydroxide, that's a typical acid-base reaction, and it's going to go to completion since sodium hydroxide is a strong base. Remember, when you have an acid-base reaction, you always end up getting a salt and water. So one of the products would be sodium acetate, and the other would be water. Okay. So what exactly is sodium acetate? Well, just like any salt, it is typically, a salt provides us the source of a conjugate base. So that sodium acetate, as soon as it dissolves in water, is going to give us the acetate ion, which is the conjugate base of acetic acid. Okay. And the sodium ion, which we're going to ignore, it's going to be unreactive and simply float around. So look what we have now. Now we have the original weak acid that we added, and we have reacted some of it with sodium hydroxide to give us the conjugate base. So now, hopefully, you can see you have a buffer system. So let's go ahead and put some quantitative calculations to that. So here's what we're dealing with. In the problem told us that we have 0.25 moles of sodium hydroxide. We can calculate moles of acetic acid, multiply molarity times liters, so we have 1.0 moles of the acetic acid. So what I would do here is simply a mole table where we have the before values before the reaction. I'm going to just rewrite the 0.25, okay? And I want to include the acetate, the conjugate base, in this mole table also because it's part of a buffer system. And so then the change, all of this sodium hydroxide, because it's a strong base, will react with the acetic acid. So the change is going to be the amount of sodium hydroxide added. Basically, that's always going to be true. And so those are present in a 1-to-1 ratio, so they're equal. And of course, we will add that same amount of the conjugate base, the product. So our final, or after amount, after the reaction, we are going to have 0.75 moles of the acetate left, and none of the sodium hydroxide. It's all going to react, and we are going to have generated 0.25 moles of the conjugate base, the acetate ion. All right, so now we're going to go ahead and plug in what we know into the Henderson-Hasselbalch equation. And so we are trying to solve for pH in this problem. All right, so pH is what we're trying to solve for. pKa is minus log of the Ka, which is 1.8 times 10 to the minus 5. And we just in the mole table calculated the mole ratio of the conjugate base to the conjugate acid. And let's see, we made 0.25 moles of the acetate ion, the conjugate base, and we have 0.75 moles of the original acetic acid left. And so now just doing the math, minus log of that is 4.74. And the ratio of 0.25 divided by 0.75 is 0.33. And so simplifying that one more step, the log of 0.33 equals minus 0.48. And so the pH, we have just made it more acidic. So our final answer is pH equals 4.26. And so what's the important message to get out of this problem? That you can make a buffer in one of two ways. You can make it in the more straightforward way, which is adding a weak acid and then directly adding the conjugate base of the weak acid by adding a salt. Or you may add, alternatively, way to make a buffer is you may add the weak acid and then add some random strong base like sodium hydroxide to convert some of the weak acid to its conjugate base. And so those are two ways you can make a buffer. You need to be able to recognize that so that you can use the Henderson-Hasselbalch. And Allie, this problem is for you. I remember one of the problems we worked from Justin's homework, even though I left it in my office. And so several of us worked it together during my office hours, but here it is for you or anybody else. But it's kind of it's not that hard of a problem, but it's got a little trick in it. And the problem looks like this. It says there's a buffer that has a ratio of hydrogen carbonate to carbonate ions equal to 5. Okay? And the first question says, what is the pH of this buffer? And they go ahead and give you Ka of HCO3 is 4.8 times 10 to the minus 11. All right, so we have a buffer, so hopefully the first thing you're going to do is write what you know, using the Henderson-Hasselbalch. Now, here's where the glitch is that most people seem to miss it. What goes on top? Okay, the conjugate base goes on top, and the acid goes on bottom. Well, if you look at our two components, which one of these is the acid and which one of these is the base? Well, they both have a negative sign, which might throw you off because it's unusual to see an acid with a negative sign. But clearly, the carbonate has to be the base because it doesn't even have a hydrogen to donate. And the hydrogen carbonate has to be the acid. So the ratio they've given you of 5 is upside down what it should be in the Henderson-Hasselbalch. Okay? Henderson-Hasselbalch says the acid should be in the bottom. Here it's in the top. So if you don't catch that, you're going to mess yourself up. So really what we have here, instead of a 5-to-1 ratio, we need to flip it upside down and 1-to-5. What else do we know in here? We're trying to solve for pH. What is pKa? Well, pKa is the minus log of 4.8 times 10 to the minus 11. And that is, let's see, that is 10.319. Okay. And that goes in here. All right. So what is the log of 1/5? Well, first of all, 1/5 is 0.2, right? And the log of 0.2 is 0.699. And so what do we have? We have pH equals 10.319. Oops, that's a minus also. Log of anything less than 1 is a minus value. And so minus 0.699 equals 9.62. Okay, so the whole key is just to remember the base goes on top and acid on the bottom. There is a part B to this problem, which I'm going to work on the next page. All right, so the second part of this question says that you add strong acid to the established buffer, and so you're disturbing the buffer, and so what's going to be the new ratio of the acid and base to each other? We know we're working with a buffer, okay, and so I would start by writing out Henderson-Hasselbalch. And plugging in what you know. So the pH they're asking us for is 9.3. We know what the pKa is from the previous page. It is 10.319, and plus log of our conjugate base to acid. All right, so 9.3 minus 10.319 is minus 1.019, and so that will be equal to the log of these, of the ratio. So you remember how to get rid of log base 10s. You do it by raising both sides to the power of 10. Right? So I will solve the math for that on the next page. All right, so 1.019 raised to the base 10 is 0.0957, and that is the ratio of carbonate to bicarbonate. Is that your answer? Are you done? Look very carefully at the problem, because the problem asked for the inverse of this ratio, just like Part A did. So how do we get that? We simply flip the answer we have. Okay, so instead of 0.0957 being the ratio, it is the inverse of that, which is 10.45. Right, so that's the pH after you disrupt the buffer by adding more strong acid.